Hi, everybody. Welcome to IPAC. This is the very last lecture of IPAC 2026. We are so grateful to have every speaker, including our speaker, Brendan, to teach us all the nice resets. So I'm not going to take too much of your time, Brendan, so go ahead.
All right. Well, thank you so much, Anna. And it is always such an honor to present here at IPAC. So, I left last time on a bit of a cliffhanger. We were talking about this kind of long and technical proof of the Fields conjectures, namely kind of the last Fields conjectures on the module structure, and in fact, the bigraded module structure of the superspace covariant ring. So the plan for today is to sort of finish this technical proof off. And, I know that not everyone is necessarily a fan of long and complicated proofs or proof sketches. So I really want to end with something which will hopefully be a little bit more pleasant, some open problems, some new directions. And right, let's get into it. So a bit of review. What was it that we were aiming to prove? Well, we had this symmetric function, c and k, that depends on numbers, k less than or equal to n. And it can be defined in a number of different ways. It's related to, for example, the delta theorem. And I gave this combinatorial definition where I'm summing up over these ordered multiset partitions sigma with n letters and k blocks. So here, I guess n would be 6 and k would be 3. And we had this kind of funny inversion statistic, which is looking for out of order numbers, but with the proviso that the second number has to be smallest in its block. That turns out to be the right thing to look at. It's not obvious, but this is actually a symmetric function. And the ultimate sort of Fields conjecture goal is that the bigraded Frobenius image of the superspace coinvariant ring SR is this sum, sort of the generating function, if you like, in the z variable of these c and k xq's. And our overall plan of attack for this conjecture was this very general principle from SN representation theory, a very useful principle. So let's say that you have an SN module, and in our context, it's bigraded. If I want to understand the symmetric function representing its isomorphism type, well, I might pair it with a basis, say the E basis. And this E basis pairing, so this paired with E mu, is equal to a certain bigraded Hilbert series. It's the bigraded Hilbert series of the image of my module under this idempotent epsilon mu, which anti-symmetrizes with respect to the parabolic subgroup S mu. And how might you try to get a handle on this thing? Well, you might have a basis, right, of V. And certainly if you have a basis of V, and if you have a linear operator from V to itself, if I apply that linear operator to a basis, what I get is a spanning set. So that gives me kind of some information. And well, we really effectively only have one nice basis of V, this Sagan-Swanson monomial basis. So what we did was we anti-symmetrized this basis with respect to mu, and then we got rid of, I would say, obvious linear dependencies, zeros, equality up to sign. And I don't think I made this point strongly enough. It's miraculous that what you get when you do this turns out to be linearly independent. If you take a basis of an SN module out of a hat, and if you perform this construction, you will not get a basis for this sort of parabolic anti-symmetrized image, right? So this is saying that the Sagan-Swanson monomial basis is actually extremely well adapted to the study of SR. So this is a miracle, and I think I should make the miracles more clear and not have them kind of hidden behind too many formulas. Um,
I'm
okay, so we have
sorry,
this. Yes.
Brendan. Make sure that you turn the iPad.
Yeah. Sorry about that. Thank you for
No,
the
you're fine.
reminder. There we go. So Sagan-Swanson monomial basis, and the way that we came to sort of understand this anti-symmetrization is via this machinery of signed partitions. where we have our partition mu of n, and we have this thing I'm calling assigning, which is just a sequence of numbers gamma I that are sandwiched between 0 and mu I. And the way I'm kind of drawing these things is like this. So here my partition is 4, 3, 2, and I have these blocks of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So the parabolic subgroup is permuting within the blocks. And gamma, my signing is 2, 1, 2. So I underline two numbers here, one number here, and two numbers there. And we have this set J mu gamma of the red numbers, in this case, 3, 4, 7, 8, 9. And if you think about what this business of anti-symmetrize and throw out redundancies means in the case of Sagan-Swanson, it means that we're looking at monomials, say just in the x variables, x1 to the a1 up to x into the an, where you have to fit below a staircase, the Sagan-Swanson condition. You should be strictly increasing in these black segments, right? Because anti-symmetrization would kill you otherwise. And you should be weakly increasing in the red segments because you're still allowed to sort, okay? So the observation that you make is that this set of anti-symmetrized sort of reduced Sagan-Swanson monomials, if I multiply by my thetas, spans the parabolic image. And we also proved that if you look at this sort of bi-degree generating function over these superspace elements, that this is actually equal to the relevant pairings with emu. And the proof here, well, I kind of pointed to a proof, really follows from a skewing formula that I proved with Mark and Jim. So we saw that to prove that the graded Frobenius image is what we said it is, it's actually just enough to get a lower bound on the vector space dimension of these parabolic anti-symmetrization images. So we want the lower bound to be, well, essentially the number of polynomials in this setup here. And the way we attacked this was we said we're going to move from SR to its associated Macaulay inverse system, SI perp. And we had this analysis of SI perp involving these kind of funny parabolic fancy D operators that showed that the vector space dimension of epsilon USI perp is, well, less than or equal to the sum, or wait a sec, important correction here, sorry, vector space dimension greater than or equal to, oh boy, the sum over all gamma of the vector space dimension of, well, the image, this is a subspace of my polynomial ring, the linear span of a certain set of polynomials E mu gamma, where what did E mu gamma look like? I gave you this definition involving translation sequences last time. And here I've written it out in somewhat maybe legible if you had 10 minutes, but incomprehensible immediately, tensor product notation, but I will have an example immediately afterwards. So E mu gamma, right?
Brandon?
Yes, thank you, Teddy.
Yeah, previous page, last page, please.
Of course.
This inequality that you reversed, is it so the gap, is it a lot in general?
Oh, the gap is actually going to be 0.
Oh, so equal.
So actually it's going to turn out that, well, essentially because of these facts up here, right? There will be no gap in this inequality. These two sides will actually end up being equal. But yeah,
Okay.
good question.
Okay.
Yeah, thank you very much. Any other questions? I know this is quick. Okay, great. So what was this kind of crazy E mu gamma set? So here's kind of a slightly different way to kind of think about what it is. Well, it depends on assigned partition, mu gamma. So here mu is 6, 5, 4. So I have the numbers between 1 and 15 partitioned into segments of 6, 5, and 4. And I have 3, 2, 3 as my signing. So I have 3 red underlines here, 2 here, 3 here. And I just wrote down the staircase. right? That corresponds to the red numbers being, well, where were you lazy? And what does E mu gamma look like? Well, E mu gamma looks a little bit like, I don't know, ordering something at a restaurant that has three courses. You have the appetizer, you have the main course, you have the dessert. And the appetizer, I guess appetizers usually are smaller. This is a weird restaurant. It's in the first six variables. The main course is in the next five, and the dessert is in the last four. So, appetizer, what you do is you take Schur polynomials S nu, where nu is something which sits inside a 2 by 3 box. So, and that basically corresponds to translation sequences where these red underlines are never allowed to go beyond the squiggly line here. Main course, you have these things that are elementary symmetric polynomials times Schur polynomials. So the Schur polynomials are always going to be in these last two variables. And they're going to correspond to motion of these two red lines in this segment of size 5, or in other words, partitions nu that sit inside a 2 by 3 rectangle. And then we have elementary symmetric polynomials in these 5 variables. And these elementary symmetric polynomials are indexed by partitions lambda that, well, can have part sizes at most 5. And then we have this funny condition on, well, how many parts can lambda have, which depends upon basically, did this red underline make it to the end or not, right? So I take this number 4 and I either subtract 1 or 2 from it to get these bounds. And then the dessert, we look at this last set of variables. We have Schur polynomials in the last 3 variables corresponding to partitions in a 1 by 3. And then we have elementary symmetric polynomials in all of the last 4 variables. And we have a 4 up here because we had 4 variables. And again, we have the number 7 here, starting my staircase. And I have 7 minus 1, 6, 7 minus 2, 5, corresponding to whether basically that this guy was able to move over or not. And these conditions might look very funny, but the thing that you should have in the back of your mind is that what they ensure is that when you expand out these polynomials, what you'll get is a linear combination of monomials that lives below this staircase. Right? So maybe that's something to think about a little bit. If you have a Schur polynomial, well, you know that the maximal possible exponent on that Schur polynomial, right, is the first part of the indexing partition U. And elementary symmetric polynomials are square free. So it's a fact. It's a little miraculous binomial coefficient identity that shows that E mu gamma has the same size as M mu gamma. And we have this final goal of proving that E mu gamma is linearly independent in the polynomial ring. We didn't have to work modulo a quotient, and that was another wonderful thing about really sort of the commutative algebra lead into the Sagan-Swanson basis theorem, that working modulo those weird I colon F J colon ideals wasn't necessary because we lived below this staircase. Okay, and that's where we ended up. So now I'm going to achieve this final goal, and well, here's kind of the cool thing. So we're looking at linear independence, not modulo a quotient, but in S. And like I said, this is a set of polynomials defined with an appetizer, a main course, and a dessert, and these are in different variable sets. And if I define any set of polynomials by multiplying together different variable sets of polynomials like this, and if I want to show that this set is linearly independent, I just have to show that these individual sets are linearly independent, right? So that's a nice simplification. And we're actually going to show something a little bit more general. So we're going to show that if k is between 0 and n, the set of polynomials that I get by looking at elementary symmetric polynomials, any elementary symmetric polynomial in all of my n variables, times a Schur function in my last k variables, where, well, I want my elementary symmetric polynomials to be non-zero. And my Schur functions are living inside this k by n minus k rectangle. I want to show that this set is linearly independent in S. And why do I want to do that? Because this will imply that E mu gamma is linearly independent in S. So this linear independence also cannot be established by triangularity, very on brand. But we're going to do one last little bit of algebraic trickery. Okay? So let's recall that we've been writing I for the usual co-invariant ideal, E1 up through En, living inside S. And we've been writing R for the co-invariant quotient ring. So we're going to use a general algebraic fact. So if B, say, subset of S, is a family of homogeneous polynomials so that B descends to a linearly, correctly? Linearly independent subset of R, then the set of polynomials of the form E1 to the A1 up through En to the An times F, where the AI are non-negative integers, and F is a polynomial in B. Well, this infinite set of polynomials now is linearly independent in S. So if you have a linearly independent subset modulo the co-invariant ideal, you get for free a linearly independent subset of the ring upstairs. And the way that you prove this theorem is you use the fact that E1 and E2 up through En is a regular sequence. So this is a relatively standard thing in sort of commutative algebra. But how does it help us here? Well, what is the set we're looking at? We're looking at, well, essentially something that looks like EA1 times EA2 up through EAN, or E1 to the A1, E2 to the A2 after En to the An, times these Schur polynomials. So applying this fact star, it's enough to show that the set S nu xn minus k plus 1 up through xn, where nu now lives inside a k by n minus k rectangle, right, is linearly independent. Sorry, I think I actually reversed this. I think we want k here and minus k here, because if I have k variables, those could occupy the first column. I apologize. So it's enough to show that this set is linearly independent in the quotient ring R. And well, how can we do this? There are a couple of ways. Maybe the fastest is to observe that all monomials in S nu xn minus k plus 1 up through xn have exponent sequences which fit below, term by term, the standard staircase. 1, 2, 3, 4 up through n. Right, so that's something you can sort of observe directly. Sort of the worst case scenario is if nu filled up this entire rectangle, and then you can check that. So monomials with exponent sequences strictly less than 1, 2 up through n, term by term, this is known as the Artin basis, right? So what I have is a collection of polynomials whose monomial expansions only involve Artin basis elements. And thus, if I call this set, I don't know, give it a name, T, linearly independent in S itself implies that T is linearly independent in R, or modulo I, because every polynomial in T has monomial expansion that lives inside the Artin basis. So that's one proof. You can also think about a geometric proof. So up to a variable reversal, this is actually a subset of the Schubert basis, right, of the coinvariant ring. So I don't know what to make of this geometry beyond that, but that might be sort of an interesting thing to look at more.
Brandon,
Yes.
something I don't understand. Yes, if you view the shoe function as a sum over semi-standard tableaus, so say mu is the whole box,
Right.
and you may have, I mean, all the columns the same.
Yeah. So
For
nu
instance.
is the whole block. So let's maybe take an example of, like, say n equals
1, 1, 1, 1, 1, 2, 2, 2, 2, 2.
Okay, yeah. So
So
n equals 5, k equals 2.
so you may have n minus k times.
So you would have n minus.
You say that this fits.
Yeah, yeah.
It
So
does fit.
5, 5, 5, 4, 4, 4, and it just barely
Yeah.
fits because I have three
I see.
fours.
I see.
No,
So
no,
it fits under okay.
it fits under the Artin staircase. No, thank you so much for asking that question, because
Right.
it's
I see.
one of the more
Okay.
pleasant parts of that proof. Okay, so this, I'll just maybe right here, concludes the proof of the Fields conjectures, namely that, say, the graded Frobenius image of SR in Q and Z is a sum as k goes from 1 to n, z to the n minus k, c n k xq. And consequently, the exterior degree d part of SR is isomorphic as an SN module to the permutation action on ordered set partitions of n having n minus d blocks up to a sign twist. So that finishes our proof for the module structure. And now the plan is to talk about sort of future directions, open problems. But before I do that, are there any questions?
Yeah, Brandon.
Yes, Teddy.
Your conclusion and your theorem of the Fields conjecture
Yes.
has two parameters, Q and Z. If I don't know if these things has been there before, but if you freeze one of the variables, let's say Q equal to 1, how simpler does a proof become?
The unfortunate thing is no simpler at all. I know of no easier way to even get the ungraded character
Mm.
than this method. And that question leads sort of beautifully into kind of my first open problem. Do we have a more elementary proof, really, of any of this? Right? So let's kind of recall at the start of Andy's lectures, when he was analyzing the bigraded Hilbert series of this ring, we had to use kind of Grobner theory in the theta variables plus inverse system analysis in the x variables. Then to prove the Sagan-Swanson monomial basis conjecture, we had to use the theory of free hyperplane arrangements in these new Solomon-Terral algebras. Then to get the bigraded module structure, it was, that this more complicated analysis of inverse systems. Is there a more elementary proof? Is there an easier way? So I don't know one so far, but this might be interesting to do. One kind of comment I'll have in this direction is, e.g., orbit harmonics. And I think I have permission to say things that are quite speculative and vague at this point. So what orbit harmonics was, let's remember from Andy's talks, was you start with a locus Z, a finite locus inside C to the N. And you have the vanishing ideal, I of Z, living inside the polynomial ring S. And any ideal in a polynomial ring, you can form the associated graded ideal, like this. And the main theorem of orbit harmonics states that C bracket Z is isomorphic to S modulo the associated graded ideal. And this C bracket Z, well, this is an ungraded object. Whereas if I have a polynomial ring modulo a homogeneous ideal, well, this is graded. And this isomorphism takes place in the category of vector spaces. And if Z has a symmetry under the action of some linear group, well, it's also an isomorphism in the category of G modules, where G is that group. So if I were to take Z to be the set of points W1, W2 up through Wn, where W is in Sn, so I view the one-line notation of a permutation matrix as a point. Well, this implies, and this was really maybe the first time orbit harmonics showed up, this is a result of constant, that S modulo ger IZ in this case is R, this co-invariant ring. So really, in some sense, the most important part, or an important part, a crucial part of this orbit harmonics method was this notion of a vanishing ideal. Right? So like this is, polynomials F and S, so that F of Z equals 0 for all Z in my locus Z. And here, what we were doing for our locus Z was we were looking at, well, I have attempt to draw this. We were looking at vertices of the standard permutahedron. So you take your type A and Coxeter arrangement, you take a generic point, and you reflect it around something like this. So these 6 red points were our locus. But there's kind of a standard way to go from vertices of a permutahedron corresponding to permutations to something involving ordered set partitions. Namely, you take the convex hull, right? You take the entire permutahedron, like so. And now you have a combinatorial object that carries a grading by dimension, that carries an SN action, and that SN action corresponds to the permutation action on ordered set partitions. So can you get something like orbit harmonics to work? Well, first and foremost, you have to make sense of what a vanishing ideal might be. So I don't remember much from my differential topology class, I'm afraid, but I remember that there were things called differential forms. And when you integrate a zero form, that corresponds to evaluation at a point. But you could think about integrating one forms, say along these edges, or two forms along these faces. And you could think about when these integrals vanish, and perhaps that could play the role of something like I of z, right? And a promising feature here is we had all these sign twists. Well, one part of calculus, right, is when you have, dxi, dxj appearing in a differential form, you negate it when you switch these variables. So, I'll just kind of say, can orbit harmonics be generalized to the superspace ring via differential forms? And perhaps instead of point loci, we really should be looking at polytopes. So that might be something that would really kind of go well beyond superspace coinvariant theory. Okay, so that was very speculative, and now it's going to get a little bit less speculative. So I'm going to let W be a complex reflection group. And I'm going to consider the action of W on V, where V is C to the N, and this action is the reflection representation. Okay. So we can let S, our polynomial ring, be the coordinate ring of V. And you can also think about this if you fix a basis as C brackets x1 up through xn, and we have this inherited action of W on S. And just to kind of review a bit of a very important, very classical invariant theory, there's a theorem of Chevalley which states that, let's see, if you look at the W invariance inside S, well, what you get again is a polynomial ring. Namely, there exist invariants F1 up through Fn. These are invariant polynomials which are homogeneous and algebraically independent, which generate the invariant ring. So complex reflection groups have the best invariance. That's why you want to study them. And Chevalley also proves, so maybe this is Chevalley part 1, and Chevalley part 2 is if I look at the coinvariant quotients, so S modulo SW plus, well, this is isomorphic as a W module to the regular representation. So we have this beautiful uniform combinatorial model that applies to any complex reflection group. Okay, so these are polynomial invariants, polynomial coinvariants, maybe a little bit of review. But what happens if we try to move to superspace? Okay. So W, my complex reflection group, also acts on omega. So I'm going to think about this as the differential forms. by which I really mean the regular or the polynomial valued differential forms on V. And you can think about this as C brackets x1 through xn, tensor product, wedge. Well, I could write theta 1 through theta n, but I'll use dxi's to be a little bit more traditional, but that's fine. And we have the usual Euler operator from omega to omega that we learn about in calculus. That's df equals the sum as I goes from 1 to n of partial f, partial xi, wedge dxi. So the action of W on S, or W on V rather, induces an action of W on omega, right? Any group of symmetries also acts on differential forms. And it's a theorem of Solomon that the W invariants inside omega are in fact a free polynomial invariant module. So the fact that the superspace or differential invariants are a module over the polynomial invariants is unsurprising because a polynomial invariant times a differential invariant is still invariant. But what is surprising is that you have this free module structure. And as a matter of fact, uh, if F1 up through Fn in S form a fundamental system of invariants, well then the set D fi1 wedge D fi2 up through D fir, where I1, I2 up through IR are running between 1 and n. Well, this is a SW basis of the differential invariance. So this is the Solomon structure theorem, and the Solomon structure theorem was actually in some sense a lemma in Solomon's paper. So Solomon used this structure theorem to prove something else. And what was that something else? It was that.
Brandon,
Yes, thank you, Teddy.
yeah, in this case you allow R to vary too, right?
R can vary too, right? So
Yeah.
this is a module, a free module of rank 2 to the rank or 2 to the n. That's exactly right.
Okay.
Okay, so what was the other thing that Solomon proved? So I'm going to let E1 up through En be the exponents of W, i.e. the degrees of these kind of fundamental systems of generators minus 1. Well then, if you sum over W in your group of T to the dimension of the fixed space of W, what you get is a product as I goes from 1 to n of T plus EI. And this identity might look a little bit funny at first, but you'll remember when you all teach combinatorics to undergrads that you prove this identity about the Stirling numbers of the first kind. So C and K, this is the number of permutations W in Sn with K cycles. And you multiply by t to the k, and what you get is t plus 1, t plus 2, up through t plus n minus 1, right? So Solomon in a paper, which is probably my favorite paper ever written in the Nagoya Journal of Mathematics, or published there. It's something like 12 pages long. He actually proves both of these results. It's just a stunning achievement. So here we have Stirling numbers of the first kind. And then when we took the co-invariant quotient, we had Stirling numbers of the second kind, right? We had, well, ordered set partitions, but still set partitions. And you might wonder, well, what happens if you look at the co-invariant quotient in type W? Okay, so we can define SRW to be omega modulo the ideal generated by W invariance with vanishing constant term, and this fellow is going to be a bigraded W module. And what do we know about it? Okay, so if W belongs to the GR1N family, so these are n by n monomial matrices whose non-zero entries are Rth roots of unity, then I'll just say that we have a monomial basis of SRW. And this basis was conjectured again by Sagan-Swanson. And the proof was joint with my student, Sutane Bhattacharya. And the proof basically starts with the monomial basis in type A and boosts it up to a monomial basis in the case of GR1N. So we have monomial bases in these cases, but aside from perhaps relatively boring cases like the dihedral cases, we don't have interesting monomial bases in general. So even GRPN, this is still open. So this is, yes,
Brandon, two
sure.
questions. So GR1N are the Riff products, right?
Oh, yes, yes. So another way I think about this
And
is
yeah, okay.
GRSN.
And about the previous result of Solomon, uh, isn't there a shift by one anywhere? So
Well,
exponents
the exponents are the degrees minus one.
are minus one, I see.
Yeah. So yeah, Solomon might have phrased that in terms of the degrees, but yeah,
I
yeah.
see, I see. Because I mean, okay,
A
right.
good question. I was thinking that too as I was writing it down, but I think I got it
Yeah,
right.
and zero is not, yeah, okay.
Okay. So right. So we have monomial bases in these cases, but I'll say open find a basis even when W equals G R P N. And somehow there are meaningful differences between the cases of GR1N and the more general cases of GRPN. Namely, if you look at the inverse systems, right? GR1N, like SN, has this magical property that you start with something like a Vandermonde, you close under a whole bunch of SN equivariant differential operators, you close under taking X derivatives, you get the whole inverse system. That was important here too. That's no longer true here, right? So your inverse systems are fundamentally going to look more complicated, and we don't quite have a great way to get our hands on them yet. Okay, so what about the module structure? Well, you can think about sort of at least for W real, I can let OPW be the Coxeter complex of W. So this is something that's supposed to behave like ordered set partitions. And it's a relatively friendly definition, like if W is S3, you just look at the type A2 reflecting hyperplanes like this. You have an action of your group W on the space. And, you just think about the way that these hyperplanes chop up your space into these connected faces, right? So we have 6 faces that are 2-dimensional, 6 that are 1-dimensional, and 1 that is 0-dimensional. And you can biject these faces in a pretty nice way with ordered set partitions. So this is kind of your picture of OPS3, and maybe I'll draw one more. So if W has type B2, you have my attempt at drawing a Union Jack. You have something that looks like this. So you have this other Coxeter complex that now has an action of B2. So this is kind of how you would generalize ordered set partitions in kind of a generic way. And at this point, we have an approximation conjecture. So this conjecture is joint with Satoshi and Andy. And what does it say? It says that for any fermionic degree D bigger than or equal to 0, there exists a W equivariant surjection from the exterior degree D part of SRW, this algebraic thing, and that's surjecting in a W equivariant way to the permutation representation on codimension D faces in OPW twisted by the one-dimensional determinate representation of W. Okay, so what can we say about this conjecture? Well, first off, thanks to Chevalier, this is true uniformly if D is equal to 0, if we don't have exterior variables at all. And not only is it true, we have an isomorphism, not just a surjection. By my work with Andy and Satoshi, this is true in type A. And not only is it true, we actually have an isomorphism. My work with Soutine says that this is true in type BC. And not only is it true in type BC, we have an isomorphism. So why didn't I just say isomorphism? Well, if you look at the data for type F4, you can consider 2 objects. So first is the exterior Hilbert series of SRW. So I'm ignoring the commuting grading and only zeroing in on the anti-commuting grading. And what you get is 1,152. That's how many elements are in the F4 Coxeter group, plus 2,304Z plus 1,396 z squared plus 244 z cubed. I'll smooth this over a little bit. Plus z to the fourth. Okay, so that's the algebraic object. But now we can look at the combinatorial thing. So this is the reversed F vector of the type F4 Coxeter complex. So we're going to get another string of 5 numbers. So this first number, 1152, is the same, and it had to be the same by Chevalley. The next number is also the same, 2304, but the next number, it's not 1,396 anymore. It's 1,392, 4 less. And the next number is not 244 anymore. It's 240, 4 less. And the last number is 1. And as a matter of fact, you can vibe code your way into not just getting the graded vector space structure, but getting the graded module structure. And it turns out that F4 has 25 irreducible characters, and the unlucky 13th character, as indexed by Sage Mathematics, accounts for just the difference here and the difference here. This 13th character has degree 4, and that is precisely the degree 4 character that's missing. So, this conjecture needs this word surjection, but even when you have something that is properly a surjection, it is somehow extremely, extremely close. This conjecture is open, I should say, in type D. And really, we would like a conceptual explanation for this. And what is the kind of conceptual explanation we might be looking for? Well, there's this theorem of Ian Gordon that says if W is a Weyl group, and Q is the root lattice, and H is the Coxeter number, then there exists a W equivariant surjection from something that looks a lot like what Garcia and Heyman introduced, namely C brackets V direct sum V dual modulo ideal generated by W invariance with vanishing constant term. So this is the diagonal co-invariant ring attached to W. 2 C brackets Q modulo H plus 1Q. This is usually called the finite torus. If we were in type A, we could think about elements in the finite torus as parking functions. So these are the W diagonal co-invariants. And we have to tensor this by the determinant representation. So Mark Heyman proved that this theorem is true and we have an isomorphism in type A. In the context of 2 commuting sets of variables, basically as soon as you leave type A, if you even go to type B and C, you have a proper surjection. So it's kind of an interesting thing. You stay a little bit more faithful to the combinatorics, right? In this superspace context of 1 commuting set, 1 anti-commuting set, 2 commuting sets, you have to be a little bit more careful. And I'll just say that Gordon's proof was indirect. It's not like Gordon said, oh, you just kind of throw these additional things into the ideal and you get something combinatorial. Still, no one knows how to do this. Proof uses deformation theory, and in particular, the theory of Cherednik algebras. And really, in terms of this approximation conjecture I have with Satoshi and Andy, I don't just want it to be proven case by case. I would really love it if there was a similarly conceptual representation theoretic proof of this result. And with that, I think I will close. Thank you all so much for listening.
Thank you so much, Brendan. That was amazing talk. Any questions?
What do the numerical, what is the numerical evidence for type D?
What is the numerical evidence for type D? I think
Probably.
for like n up to about 6, but it's been a few years since we've tried that.
In
In the numeric
isomorphic.
and it's isomorphism. Yeah. So for all we know, it might be an isomorphism in type D. That could also be true. But the proof techniques are going to have to change in a pretty significant way in type D.
Type D is tricky. Sometimes there's a difference between even and odd values of n.
Yeah, and I mean, I don't know somehow if we don't want to just consider the determinant character, but another like one-dimensional character in type D as helping to generate the inverse system. But this is very speculative. So
Any other question for Brendan?
Brendan, thanks for the nice series of talks.
thank you very much, Sean. And by the way, I should mention Sean, together with his co-authors Maria Gillespie and Eugene Gorski, have a representation theoretic model for the QT delta conjecture. But this model, it's a Springer theoretic construction. It's not as simple as like an action on a polynomial ring. And it would be really cool to see if there are connections between this and the geometry that they did. I hope I got that right, Sean.
Yes, thanks for the shout out. I wanted to ask a different question. I think maybe we've chatted about this before, but um, this is like um, the symmetric group character, the Frobenius characteristic of this thing is the delta conjecture, um, like all the delta conjectures combined for at t equals 0.
Mm-hmm.
Do you know if anyone has a corresponding GL representation whose character is that symmetric function?
Oh, like the sense of Kato or something. Yeah, so I don't know. I think that I would first really have to understand even the co-invariant story before answering this intelligently. But no, I'm not aware of a GL module. I mean, one tricky thing is like, what is a theta variable in GL representation theory context? Like usually you think of these X's as being eigenvalues of diagonal matrices that are acting. But if an eigenvalue, if a complex number squares to 0, I think that complex number has to be 0.
Hmm.
So I don't really know the role. Like the theta variables would have to play a very different kind of role.
Right.
All right. Any other questions? If not, let's thanks Brendan again. Thank you so much. And thank you so much for joining, everybody. See you next year. Have a nice fall semester. Bye.